Right. Physics 30, today's lesson is consider it as refraction part 2. It's specific mathematical formula that we are going to use, Snell's law. I believe the only thing that is changed between old curriculum to new curriculum is old curriculum used to put these four as equal together, but I think the new curriculum have a little two formula instead, like first one like this, second one like that, if I recall. So please double check. So Snell's law basically is a convenient way that you can figure out the speed of light or wave between one medium to another, wavelength of a light or wave from one to another, and angle of incident and refracted angle, which is conveniently use it as 1 and 2 instead of I and R. Basically, we're using this mathematical relationship between those, and Snell basically summarize it for us so that we can easily use. One thing that I like to emphasize again is frequency does not change once it leaves the source. So frequency 1 and 2. In fact, wavelength and speed change to compensate that mathematically if you like to go through in that way. So let's think about an example over here. It's not specifically example, but you have an incident angle, which from now on I'm going to call it theta 1, and refracted angle, theta REF. Now, as you may notice in this situation, I have angle, and seems like my angle 2 is a little larger, so that means it's less packed, it's more packed situation. Whenever that happens, you guys know that, and 1 more packed, which is more dense, thus a higher value of n. You need to understand theoretical connection between, and we're basically going through that as a class over here. So, example, 630 nanometer light enters into glass as shown. If the index of fraction of the glass is 1.54, determine the angle of refraction and those kind of things. Now there is one that I mentioned last time. I believe I used 300, but I'm gonna give really specific situation. If you're dealing with visible light spectrum, you need to understand that the wavelength is always around 340 to 750, let's put it that way, if I'm being really precise. So 350, that is really low wavelength, 750, that is really large wavelength compared to these two. Larger one you can consider as red, smaller one violet, because anything below that is known as UV, anything above that is infrared red, IR. So 630 is falling between those. It's in fact somewhere in the middle to farther left, farther right of the spectrum. So it's kind of like green to blue, green bluish color, 630 nanometer. Although the question didn't ask you about that theory question, but I just want to double check your understanding, and like I mentioned, you need to memorize those. I believe I mentioned 300 to 700, but in real life, if I really being anal about this situation, 350 to 750 is an actual. But in any case, I have 18 degree that is happening between the surface and my radiation over here. So I need to find out my theta 1, which is 90 minus 18, which is 62. Actually, it's 72. My bad. 72. Always double check your mental math, folks. All right. We know that the index of the glass and 2 in this case is 1.54. Error is not given, but you know that its smallest number 1.00, so we can put those two. We know the velocity 1 is 3 × 10⁸ meter per second. V2 we don't know. In fact, I'm writing all of the clue, only some that I'm going to use. Let's see, enter into the glass. We need to find out the angle of refraction. Now, first thing first, we're going less packed to more packed. So that means angle should be relatively smaller. I actually draw it really small. Instead of refraction, I'm gonna put theta 2. Honestly, it will be slightly bigger than that, but let's say, as long as it's larger to smaller angle, you're on the right track. Now let's go back to our Snell's law. What will be really good, useful part of the formula? Well, sine will be really useful because in the end we're trying to find this angle over here. So I'm gonna use these two. Next two. There are several parts, but you have to use n2 over n1 situation because number one, we don't know the velocity of those. We can find velocity and use it, but why bother go to two-step method when you can do one step? And even if wavelength is given, well, I'm not gonna find out the, I'm not gonna find out the whole wavelength again unless it's asking specifically. So I'm gonna use my A part using the sine and n part of formula. Sine theta 1, sine theta 2, and 2, and 1. And I'm going to isolate everything. Sine theta 2 is equivalent to sine theta 1 times by n1 over n2. Now, let's punch some of the number in. Sine 72 degree times by n1, which is 1.00, divided by 1.54 will give me a nasty number. Don't forget to change into degree mode, by the way. Holy moly. Don't put as a radians. So, we get that nasty number. Now what I need to do is second function tangent and put that value in there to get my theta number 2. So second function sine and put previous answer. That gives me 38 point, what is it? Oh yeah, 38.1 degree. And that is what you need to find out. So as you may notice, the angle is definitely smaller. I believe this is a part where I did a little bit of a wrong answer in my PDF file, so just have it in your mind. This is a correct answer. Frequency in the glass. Now, in order to find the frequency, one you need to understand is we're going to use V is equal to F lambda. If you want, you can change it into C if you want. But in any case, we need this, which means Y giving you 630 nanometer is now makes sense. What I'm going to do is, because we rounded up the angle, let's just use something that we know for sure. N2 over N1, that is equal to lambda 1 over lambda 2. And we're trying to isolate for lambda 2, so it should turn out to be like this. And now we are simply putting every value in here. Lambda 1 is 630 10 to the power negative 9 meter, and 1, which is my 1.00, and 2, 1.54, gives me, this time it's kind of pain in the butt to move everything around, so I'm just going to punch the number in, folks. About 4.09 10 to the power of negative 7, which is about 409 nanometer. But we're going to use that. 409, so it's relatively close to, I think it's close to like orange to yellow, somewhere over there. So light changes. Sorry, the EMR spectrum changed a little bit. But in any case, since we know that, we can actually find out CF lambda, except the only problem is, again, we need to have this V2. We're trying to find a glass frequency, glass, and then a speed of light in there. So I'm going to use basically same type of calculation, n2 over n1, that is equal to v1 over v2. v2 is n1 v1 over n2. So if I just punch the number in, that's 1 times 300 10 to the power of 8 divided with 1.54, you have about 1.95 10 to the power of 8 meter per second. And please don't try to round up some of the number when you now punch the number in, ladies and gentlemen. So now I'm going to find out the C, which is V2 over lambda 2. And that's what I need to punch the number in. This 1.95 10 to the power of 8 goes on the top. 4.09 10 to the power of negative 7 go at the bottom. Again, try to use the number that you preserve in your calculator. Then you have 4.76 10 to the power of 14 hertz is what you have. And that's what you need to eventually have it. That is an example. Now, critical angle. Diploma love giving you a question like that nowadays. I'm gonna tell you what that means. Critical angle, specifically talking about special incident angle, ladies and gentlemen. Because when people say it's critical angle, that means the angle of refraction is always 90 degrees. So it is always 90 degrees as going off. So funny thing is, my incident radiation come to the angle, but after hitting a surface between the medium 1 and 2, it straightly goes off. So there's no bigger angle than 90 degrees for the refraction actually. If it's more, then we call it internal reflection, sorry. This is the part where incident is greater than critical angle. But again, let's not talk about total internal reflection right now, because to be fair, when it comes to calculation in diploma, they ask you 90 degrees most of the time. And you may notice that sine 90 is always 1. Just for the heads up. People who did math 30-1 probably understand about this. Now, that means my critical angle, which is my special incident angle, it's always smaller than 90 degrees. So, if you think about N1 and N2 situation, you're always more packed to less packed situation. So, N1 is always bigger. That's what I want to point it out. So, if I use the relationship that we know from Snell's law, here's what happened. Sine theta c over sine 90 degrees is always N2, N1. That is a modification for your critical angle. Have that in your mind. It is the exact same thing, you're just approaching it a little differently. And if the angle of incidence is somehow greater than the critical angle, then that's where it go over 90 degrees. So technically, refraction is out of the picture because you're coming back to where you come from. So it's reflection. And total internal reflection generally cannot occur when the ray go from fast medium to slow medium. It's because you guys need to remember, if I want to go with the bigger angle, that means I need to go with less dense. So that means I need to go to slower speed to faster speed, not the other way around. Faster medium to slower medium, we're not going to make that happen. And the ray will bend towards a normal. And even when the incident angle is very large, like 89, close to 90, there will still be some kind of refracted ray in reality. So let's do critical angle question situation over here. Now, a critical angle for air diamond surface is 24.3 degrees. How much time would it take for light to travel through 5.71 centimeter diamond? Include a ray diagram. So, let's draw a situation actually. Straight as possible, air and diamond. Air and diamond. We have 24.3 degrees that create critical angle. That's about that. And refracted one is easy, 90 degrees, theta 2. Now, it seems like how much time it takes for light to travel through 5.71 centimeter diamond. Well, that means the diamond distance that is traveled over here is 5.71 centimeter. That's D, and we're asking to find what's the time. So in the end, we're going to use this again. Oops, that means we need to use our speed inside of a diamond. So let's go with our formula. Sine theta 1 sine theta 2 is equal to V1 V2. Let me quickly double check. And it is correct. V2 is what we need to figure out. So modify this. V2 is equal to V1 sine theta 2 over sine theta 1. And now let's punch the number in. It says air, so V1 is 3/10 to the power of 8 meter per second. Sine angle 2 was sine 90 degree, which is like 1. And sine initial, which is sine critical angle, 24.3 degree. That should be the correct answer for the velocity. So let's punch those number in. It's kind of like 1, but in any case. Then you have, I'm going to round it up a little bit. Yeah, sorry about me constantly hitting this gooseneck holder. 7.290, 10 to the power of 8, somewhere over there. Again, keep the speed because you like to use it. That's my part number 1. Part number 2 is now I'm going to use for VD over T, except I'm gonna modify in terms of D over V. That's what I'm gonna do. When it comes to distance, 0.0571 meter. And when it comes to speed, 7.290, whatever that is what I need to put for the time. So 0.0571 divided by previous answer should give me about 7.83 10 to the power of negative 11 second. And I'm putting as a significant digit for everything. That is my answer. Now your to-do list, basically doing every question about Snell's law and critical angle, because diploma question love giving you type of the question that is involved with Snell's law and critical angle. I want you to give it a shot for that. Thank you.